Hello, everyone. This is section 2.3. Bear with me today. If you notice the time, I'm thinking this lesson is going to be a little bit longer than some of the other lessons. I apologize for that. I'll go through it as quickly as I can, but there's a lot of information. We're going to try to split this up into two, but then the timing didn't work great for the test that we're going to have next week. So 2.3, there's a little bit of repeat in 2.3. It's more about displays and other things. So I'm going to go through some of this a little quickly at the beginning. Some of these are just what I say are keywords from section 2.3, and I'll just try to do a little reminder with there. Just kind of ignore that. So little formulas here. Sorry, that's a little small. Let's make that a little bigger. Ignore that. The average, I think you all know the word average or mean. Add them all up, divide by however many there are. Nothing new there. The median, we talked about already. That's the value that divides the data in half when the data is in order. So sometimes we don't give you that data in order, so make sure you put it in order. The quartiles, we've talked about the quartiles, splits the lower and upper 50% in half when in order. Quartile 1, sometimes called the lower quartile. Quartile 3, sometimes called the upper quartile. These numbers are going to become important again in just a second. That's why we're repeating them. The minimum value of a data set is just the lowest value in that data set. The maximum is the highest value. We got a little typo here. Sorry. This is called IQR, interquartile range, middle 50%. Quartile 3 minus quartile 1. Just find the third quartile, find the first quartile, subtract them. Just put this little note there that this is a number. So if I ask you, what's the interquartile range? You don't say it's from 10 to 15. You say it's 5. So the problem with interquartile range is it doesn't tell you where it is, right? But it just tells you how wide it is. So don't give me the from here to here. You might say the middle 50% is between 10 and 15. That's good terminology and a good use of shape, center, and spread terminology. So we get this thing called a 5-number summary. The 5-number summary is just the minimum value, the first quartile, the second quartile, the third quartile, and the maximum. Another terminology is just the range. The range of a data set is just how far it is, maximum minus the minimum. You find the biggest value, you find the smallest value, which you probably already found that 5-number summary, and you subtract. Again, it's a number, so you don't say the range is from 60 to 100. You say the range is 40. Okay. So we're going to talk about box and whisker plots and outliers sorted together. So let me do box and whisker plot first. A box and whisker plot is another really nice display. Some of you have seen it, maybe some haven't. Sometimes it's called a box plot. Sometimes it's called a box and whisker plot. And all that is a 5-number summary on a scale. So what you would do, I'm going to try to draw a little picture here. Let's say you had this scale from 50 to 100. Maybe they were test scores. And let's say the minimum was 60. Let's do a little bit better than that. Sorry, we'll have a little bit better scale. We'll go 60, 70, 80, 90. You always want to make sure your scale is uniform. Don't be jumping numbers around. Otherwise, it skews the data. You can't tell what it looks like. Whoops. So let's say the minimum test score was 60. Let's say the first quartile was 70. I'll just make this easy. The median was 75. Don't worry, our tests will always be higher than that. And the third quartile, let's say maybe that's 90. And then the maximum, let's say someone got 100. So this is what's called a box and whisker plot or a box plot. That's the box. The box is the interquartile range from the first quartile to the third quartile. It has the median there also. And then these are called whiskers. You just put these little whiskers on there. You can kind of see the data is a little skewed to the right, maybe, just because of the shape of that. Okay. So outliers is a specific term. We've kind of been vague about it before, right? What's an outlier? So an outlier actually has a definition. And an outlier, this is a little hard to read here, but an outlier is anything that's more than 1.5 times the interquartile range from the nearest quartile. I'll do a little math for you here as an example second. It's anything that's more than 1.5 times the interquartile range away from the nearest quartile. So if I had a data set, okay, I'm just going to make up a data set here, so I'm not going to actually do a lot with it. So let's just say it had a minimum of 60, first quartile 70, we'll just make it really easy here. 80. And then the maximum we'll put over here at 100. So what you would do is find the interquartile range, which means you'd have to find the first quartile and the third quartile. So for my particular example, my interquartile range is 10, goes from 70 to 80. After you find the interquartile range, you multiply it by 1.5. Okay. So I should have put my little whiskers on there. That gives me a 15. That means anything more than 15 away from the quartile. So what you do is you take the first quartile, which is 70, and you subtract that 15. So 55 is kind of the cutoff for the quartile on the left side. So if anything was less than 55, it would be an outlier. You take the third quartile, which is the 80, you add that 15, you go the other direction, gives you 95. So anything more than 95 is an outlier. So in our data set, we'd have at least one outlier. Remember, we know the maximum is 100. I don't know if there's other ones, but we'd have at least that one outlier to be 100. So that's how you figure out what an outlier is. There's another little terminology. There's actually something called a modified box and whisker plot. A modified box and whisker plot just actually marks the outliers specifically. So I'll show you what I mean by that back on this one. If I wanted to do a modified box and whisker plot, I would redo this picture. I'm just going to be really quick here. 60, 70, 80, and 100. We know the 100's an outlier, so we just mark it separately. We still have this thing from 70 to 80. And then let's say there was another outlier, maybe at 99 or something, and then you draw the whisker and you stop it at whatever the largest number is or the smallest, and they said that's not an outlier. So you mark the outliers separate and you draw that whisker up to the next one. That's called a modified box and whisker plot. All right, let's move along. I know it's a long one, sorry. Percentiles, you probably heard percentiles. Percentiles are the values that separate the lowest percent. So if you're, say, the 90th percentile, that's the person that's in that spot 90, everything below it. Okay, you've probably heard that terminology before. First quartile, then, by definition, is just called the 25th percentile because there's 25% of the data below the first quartile, which means the median is the 50th percentile, and the third quartile is the 75th percentile. Percentiles give us a way to draw a little thing that's called a cumulative frequency or percentage plot that you see here. And what that is it just tells us the quartile. So I try to draw these in. What you see is this little plot that kind of follows a graph. These are like SAT scores. And so if you go to, this is percent on this side, right? So if you go to like, this is the 30th percent. So if you go 30% over here, the 30th percentile is a score right around 460. If you wanted the median, you go to the 50th percentile. The median is somewhere right there, and then 75th. So you can find any percentile. So you could actually find the minimum, the maximum, the first quartile, the median, the second quartile from this. Okay. Next is measuring spread. You've probably heard this term standard deviation before. Standard deviation is terminology for roughly how spread out a data set is. We use this letter S or SD sometimes for standard deviation. We'll talk about notation a little bit more as we go through the class. I don't know if you've seen this formula before, but standard deviation has a formula for it. And what you do is, here's the formula. It's actually on your note sheet also. It's a summation of each X minus the average squared, and divide that by the number of data points minus 1 and take the square root. I'm actually going to do an example problem for you here in just a second. So I know that might be a little confusing, but I'll walk you through one. We just have some terms. This is called a deviation. A deviation is just how far something is from the mean. So it's just the data set, the data point, which is X. So X represents all of the data points, and X bar is the average. In a data set, the sum of the deviations will always be 0. You'll have the same amount of numbers or differences on the positive side as you would on the negative side. Another notation which we'll deal with later is S squared, or sometimes SD squared, and that's called variance. All right, so I'm going to do a quick example of how to find standard deviation. Whoops, I'm actually on another sheet. Sorry about that. Standard deviation example. Okay, so I just have a quick data set, 4, 5, 6, 7, 8. The formula is right there for you. I'm going to show you how to find the standard deviation. The first thing we need to know is to find the average. 4 plus 5 is 9, plus 6 is 15, plus 7 is 22, plus 8 is 30. I made that work out nice for you. You can use a calculator. It's not always going to work out nice for you. So 30 divided by 1, 2, 3, 4, 5. So the average x bar is equal to 6. So normally when I do this, I'll just write a little chart. I'll put my x's. Remember, x is all my x's. And then I'll find the deviations, x minus x bar. So it's minus 6. So 4 minus 6 is negative 2. 5 minus 6 is negative 1. 6 minus 6 is 0. 7 minus 6 is 1. And 8 minus 6 is 2. Notice those add up to 0. They always will. Then we want to square these. 4, 1, 0, 1, 4. Then we want to add them. Then we want to add them all up. Oh, sorry. My little script was bad there. Let me fix this. Let me do a little erasing there. The little summation should be on the x minus x bar square. We're going to add all those up, and then we're going to divide by n minus 1, and then we're going to take the square roots. All right. So let me take one quick peek here. Yep, sorry. Okay, so we're going to add them all up. 4, 5, and 1 is 6, and we got 10. We're going to take that 10. We're going to divide it by 6. Oh, not 6, sorry. By 1 less than the number of terms, which is 1, 2, 3, 4, 5, which is 4. Good math there. And I think that's 2.5, right? And then we take the square root of that. You can use your calculator to do that. That's how you find the standard deviation. It's just a rough measure of how spread out a data set is. Okay. All right. Here we go. So we've talked about this terminology before, like when you're going to summarize things, like what do you use? So we got all these words: mean, median, standard deviation, skewed right, skewed left, spread, middle 50%, normal. It's a little hard to decide. I mentioned this the other day. Typically, the only real decision is mean versus median, but the median's typically a little easier to find, and it's also usually a better thing to find because if the data is skewed, the median isn't affected as much as the mean is. Okay. So a couple other terms here: recentering and rescaling. Recentering is if you take this a number and add that number to every point in a data set. Typical thing to do at test scores, maybe if a teacher thinks the test scores were too low, maybe they just add 10 points to everyone to raise the average, right? So if you add or subtract, so I should say add or subtract. Just want to tell you what happens to all the important information when you do that. So C is the number I'm adding. All right. So what happens is, sorry about that, the shape of the data set, the spread of the data set do not change. If you can see my video here, you just take the data set and it's just moving over, right? So it's still the same shape. It's still skewed right or normal. The spread, like the middle 50%, is still the same distance. The range is still the same distance. The standard deviation is still the same difference. So nothing, all that spread doesn't change. The only thing that changed, sorry about this, this should have been, the only thing that changes is the new mean and the new median. The new mean and the new median will be the old mean plus the C or minus, or the new median would be the same, the old median plus the C. Everything else stays the same. Rescaling, however, is when you multiply every value by C. That now changes the shape, okay? Because bigger numbers get more bigger, right? If you multiply 100 by 10, you get 1,000. You multiply 90 by 10, you get 900, right? So the difference between 90 and 100 was only 10, but the difference between 900 and 1,000 is 100, so it gets more spread out. So if you multiply everything by C, you could also shrink it if you multiply by like 0.5 instead of by 10, okay? So we always say that C is positive. We never would multiply numbers by a negative number. But what it does, the basic shape will still stay the same. It'll still be roughly normal or roughly skewed. It'll just be more spread out. If C is greater than 1, it'll be shrunken more if C is less than 1, okay? Everything gets multiplied by C. New mean, new median, standard deviation, range, interquartile range, all of that stuff is the old one times C. It all gets more spread out or less spread out if you're multiplying it by less than 1. Okay. Just a little quick kind of terminology. And then one last thing, take a little sip of water here. A summary statistic is resistant to outliers if it doesn't change much when you remove the outlier. So a lot of times mathematicians worry about outliers. Give me 1 second here. Just don't look at that next thing. A lot of times mathematicians are worried about outliers. Like, do they affect, like, you might be worried too if you're a student and a couple of people get 100 and that messes up the average, that sort of thing. If you take out those numbers, if it doesn't change the set much, it's called a resistant. So like a median won't change very much. If you have houses and you take out the biggest price house, the median's not going to change, but the average would. Okay, so if it doesn't change much, it's called resistant. If it does change, it's called sensitive. So we have all these things like standard deviation, range, interquartile range. Like the interquartile range won't change at all if you take out the outliers. So that would be resistant. Okay. And then sensitive is if it does change. And then the last little thing here is we'll see these little charts quite a bit. This is called a frequency table. This is a frequency table that came from a bunch of families, and they were asked how many kids they have. So we might want to find the mean and standard deviation of this. So often, like if you go to if you go back to this example, 4, 5, 6, 7, 8, it was just a list of numbers, right? So if you think we go to this is just a list of zeros, ones, twos, threes, fours, fives, six, sevens, and eights. There happens to be 15 zeros in that list and 22 ones in the list and 25 twos in the list. So we clearly don't want to go through that process we went through to find this standard deviation term by term by term, but you can do it by just in this frequency table. So notice, if we do this, I'm going to do a little quick math. Sorry, I didn't do this before. What I'm going to do is, so I'm going to find the average number of kids per family. So the average number of kids per family is, remember, there's 15 zeros and 22 ones and 25 twos and 18 threes. So you take each one of the frequencies and you multiply it by how many there are, and then you divide by the total number, right? So I didn't add these up either. Sorry, I'll do this quick. 37, 5, 7, 12, 20, 22, 26, 20. I'm thinking this is 100. Yep, I think we got 100 people, 100 families. Okay. So I'm going to find the average. So I know you can't see my calculator, but what I'm doing right now is just 15 times 0, 22 times 1, plus 25 times 2, plus 18 times 3, plus 4 times 10, plus 10, plus 24, plus 14, plus 16. So I just added them all up. I got 230. I divide it by 100. So the average is 2.3. I'm not going to go through all this work with you right now because I know you want to watch this. But what you would do next, remember, is you would do x minus x bar, right? So you would do 0 minus 2.3, and you get negative 2.3. Then you do 1 minus 2.3, you get negative 1.3. 2 minus 2.3, you get negative 0.3. 3 minus 2.3 is 0.7, and so on. Right, so we do that first. Notice the formula here. Same thing we did before, but we just got a lot of zeros, right? We got 15 zeros. Then what we do is we square them. Okay, I'm not going to do the math for you. You square them, and then once you square them, this got left out here, sorry. You got to multiply by the frequencies because remember, it happens 15 times. So I'll do the first one for you. I'm going to go to 2.3 squared. And then then I'm going to square it, and then I'm going to multiply it by the frequency. So I'm going to multiply it by 15, and I'm going to get 79.35. You would do this for all of these. I am going to show you a quicker way to do these in class later on, but for right now, you just kind of got to go step by step. So I think that's it for section 2.3. Sorry, that one's a little bit longer. Hopefully I didn't go too fast. Please, let me know if there's any questions. Have a nice afternoon or evening or morning or whatever it is when you're watching this.